almost for the last 30 years.
Yeah.
Nice studies. And I think this low dimensional system, with these advanced capabilities can open up, new horizons. I think I totally agree with you on that.
Okay, Saptarshi, that's excellent talk. So I have a couple of questions. Okay.
Sure.
So I will start with stochastic resonance, and then I'll go to very, very fundamental things. So what is the role of persistent photoconductivity in this, stochastic resonance in your case?
So here we are actually not taking into account persistent photoconductivity. I think it will actually destroy your system because you have memory.
Yeah,
right?
Exactly. That's what I was thinking. So you make sure that this device, they don't have persistent photoconductivity.
So here we have to take care of only the photo response. So which happens in the, so I mean, if I go back to this slide, actually, one of the slide I was showing. So why I feel like these 2D materials are very interesting is that if you remember this slide, let me go back here. So you can see that, if I illuminate my device in the on state, okay, then I get only photo response, which means there is no photo gating effect because I am not enabling any trap states in my alumina. So there is no carrier capture. So whatever is generated simply drifted out, of the channel. What happens is when I illuminate in the off state, then although the electrons can get released, because these are Schottky barrier devices, my holes cannot really get released. And then they get much higher chance of getting captured by the alumina. And that results in a threshold shift. So depending upon at what condition you are illuminating, either you will have persistent photoconductivity or you will not. So here the device works like just a normal photo sensor, right? So response up and response down. And that is what you need for the stochastic resonance. If I try to use this for the stochastic resonance, it will not work.
Yeah. And another thing, like, when you are working with 2D materials, there's this contact is a big issue in this case. So how do you what kind of contact do you prefer? I know that during your PhD work, you have some pioneering work on this contact material with 2D. So what is your kind of, these days, what kind of contact material you think is probably best for these 2D materials?
So, there have been champion papers out there. I think there was a recent paper in Nature that came out from a group from Hong Kong University.
Is it bismuth?
Bismuth contact, yes. You already know about that, yes. Yeah. So that is the record low number.
Yes.
123. There is another paper that, I recently reviewed. It's going to come out in Nature Electronics where they say, actually, when you're growing these 2D materials, you get a lot of sulfur vacancies.
Yes. Yeah.
But if you can really terminate those sulfur vacancies using some kind of an oxygen, typically we feel like, oxygen exposure to this 2D material is bad. But this group from MIT have now shown that by actually doing the growth in the presence of a little bit amount of oxygen can heal those sulfur vacancies. And that leads to better photoluminescence, photo response, as well as better contact resistance.
So that is during the growth?
During the growth. Typically,
see.
When I told it to my colleagues, at Penn, they said, we don't want to introduce oxygen, right? We want to
because I think Robinson is there, who is, kind of famous for this CVT
growth. Right. So we might actually try it. I mean, this paper is going to come out probably in this month's issue of Nature Electronics, which was actually quite interesting to see. But at the end of the day, the contact issue for MOS2 has been resolved to a certain extent, I can tell you. With titanium or nickel contacts, we can get down to low contact resistance. But at the end of the day, to compete with silicon, you really need to think about degenerate doping of this 2D material underneath the contact. And that has not been achieved yet. We're trying, but unless we can do that, just this 1 or 2 papers with bismuth contacts or this contact, that contact is not going to make a technological sense. These are good for a demonstrative purpose. It shows that it can be done, but really in order to scale it up, we need to make sure that we have degenerate doping of this 2D material. And that's what we are working with my colleagues actually to see how we can essentially degenerately dope this 2D materials under the contact area. That will be the ultimate rescue for the contact resistance problem.
Yeah, there are some reports that they, expose it to argon plasma and form it to metallic state, and that probably can do. But I think it's not very reproducible or well controllable. That is
Yeah,
only.
I mean, it is just, one or two groups have reported, and then I think it's not been like a scalable technique.
And also, I think it's not very reproducible at the same time. I mean, even if you're getting it
Reproducibility and
once, it's not.
scalability are big
Yeah,
issues.
yeah, yeah.
Yes, yes.
Because we even tried, and the results are kind of random.
Yeah. I mean,
Um,
that's true. I mean, yeah, agreed.
Another thing, kind of people who are working in 2D, there are two, kind of schools. One using all the exfoliated material, and another large area sample, CVD, MOCVD, all those things. In case of these kind of applications, what do you think? Because in certain cases we need some defects in the material itself. Okay, so what do you think? The exfoliated one is better for this kind of applications, or the CVD or MOCVD grounds are fine?
So right now in our group, we are primarily working on large area. I mean, that's because I'm in Penn State. So by virtue of being at Penn State, I work with large area 2D materials. But you are absolutely right. It is very application agnostic, because the quality that you get from an exfoliated material, we are yet not there. I mean, MOST is almost reaching there, but the other 2D materials are definitely not there. For twistonic devices, right? I mean, that's like the hot field right now.
Yeah.
I don't think there is any rescue other than using exfoliated 2D materials, because I mean, the interface has to be really perfect, right?
Yeah.
And that too, people struggle. Even with exfoliated material, people struggle. So I don't think large area material can really be really beneficial for these people who are working with Twistonics, at least not in the next 2-3 years. I can't see that. But for many of the applications that we are doing, let's say, for example, optoelectronic application, we are also now looking into defect engineering. We can now create, single defect, vacancies or whatever it is. We can actually have, I mean, it is not completely controllable yet, but we can create, these defects or defects engineered 2D material at Penn State. And that could essentially give rise to, better photoluminescence property or excitonic properties. In some cases, we have seen, this vanadium dopant gives rise to magnetism. In some cases, even ferroelectric properties and things like that. There's been prediction, all sorts of predictions, right? So defect engineering is a viable option. It is possible, but again, the control is going to be tricky. It is not really controllable. So that is the second school of thought, essentially, can I do defect engineering? And then I would also add a third school of thought, which is, we are trying to make everything perfect, right? And trying to make sure that all our 1000 transistors that we are making, all of them work. Right now, the problem is not that much in the growth. The main hurdle is actually in the transfer process, because you have to always transfer this 2D from sapphire substrate onto your growth on any application substrate. And if the transfer goes wrong, then your device's yield will go very low, or device properties will be very, very poor. So it is not only developing the growth technique, but also we have to develop a very good transfer technique in order to really fully utilize the application of these 2D materials in large area application, or whatever we do with integrated circuits.
Yeah, I completely agree. And also, I think this large area grown samples. I mean, that's my thinking is probably good for these neuromorphic devices or memristor type applications. Okay, again, probably due to the defect engineering and the possibility of defect engineering, because I think a lot of work in the memristor or neuromorphic devices are actually done on this CVD grown or MOCVD grown MOS tools. So in your group, you're using these neuromorphic applications all in these CVD grown samples or MOCVD grown samples, basically.
Yeah, mostly MOCVD and CVD grown samples. Yeah, but I think I can also tell you that, one of these studies that we have done, and I think you will also see that a lot of work is coming out of IMEC. And
Belgium,
recent paper that is coming from Intel, actually, where and TSMC has already put in 2D materials in their roadmap. So which were actually very surprising, very happily surprising that TSMC is talking about 2D materials in their roadmap. So I think the industry is now becoming a little bit serious about this 2D material, because they have also sensed that it is just not, kind of this hype that has happened with a lot of other nanomaterials.
Yeah.
There might actually be some promise. And I think these benchmarking studies actually show that we can actually reproducibly get good quality of materials. And in fact, I can also tell you that, I mean, these devices we have made like 2 years back, they actually work pretty well now. Sometimes their performance actually improves over that time. And that kind of goes along with what the MIT group is telling, oxygen may actually heal some of the defects. And over the period of time, it can actually become a little bit better. So monolayers of this 2D material, even if you keep it in air, they survive for like 2 years. That tells me that these materials have potential. I mean, when you see things as surviving for that long without kind of degrading, and these are all large area grown material, right? So that I feel like might be some promise with the 2D.
Excellent. Okay, Saptarshi, thank you again. Yeah, it sounds excellent talk.
Thank you for the questions.
Sir, I have one question.
Yeah, sure.
Yeah, so regarding the part where you showed detection of a periodic signal from the white noise. In a more real life scenario, you might have white noise from multiple sources, right? Say for when you detect a car approaching, or the example you gave. So in those cases, the threshold you set to detect the signal, that has to be dynamic, right? Because the multiple white noise can add themselves to give a spurious signal, desired signal, which may not be the case.
Okay. I see. I mean, that's a good question. I mean, but I think there are two different things. I feel. I mean, the collision avoidance scenario is very different, right? I mean, there we are not taking into account any of the stochastic resonance idea, right? I mean, it is just using the photo getting effect, the photo response, and then we are using some programming to detect the information. So in those scenarios, even if you have noise, I mean, my device will be agnostic to that noise because I'm really exploiting the photo responsive capability of my device, right? So I'm not talking about very low intensity of light. So that scenario is different. When it comes to the stochastic resonance, I mean, I think you're absolutely right that in order to make it apply to the real life, I mean, these are very good scientific studies. There has to be a lot of fine tuning, right? So stochastic resonance actually requires a fine tuning because without really knowing the strength of the signal, in this case, we knew the strength of the signal from before, and therefore we knew what kind of noise can actually enhance that signal. In a real life application, you might actually have to essentially do, different noise for different period of time and see if you can discover that signal, right? So that kind of a tuning has to be done. So it's not a straightforward answer. I mean, I can't give you a straightforward answer because the math of stochastic resonance is actually also very involved.
So in those kind of scenarios, the strength of machine learning can also come into the picture, right? Because
you can use that. Yes, you can use to train your system, knowing from previous iterations that what kind of noise intensities I have used to discover my signal to essentially then use. I mean, and what I didn't talk about in this lecture is that we're not only using stochastic resonance. Along with stochastic resonance, we also use principles like population coding and population voting. Okay, and they can also help you to kind of sort out some of these uncertainties with stochastic resonance. So I agree with you. Machine learning and incorporating other kind of algorithms would definitely help and augment the detection using stochastic resonance.
Thank you, sir.
Hello, sir.
Yeah.
So in the towards the last part of your talk, you talked about this noise of LEDs for detection of the signals. So you said that too much noise is not good and low noise is also not good. So is this means how can you control the? Can you really control the noise that LED puts in the system, or means how do you control it?
That's a good question, actually, right? I mean, how do you control the noise? And since I do not know what is the standard deviation of noise that will be needed. Now, I mean, there have been also studies. In this particular case, we have actually used white noise. But I think in the past, people have also studied, other colors of noise, pink noise, gray noise, brown noise have also been studied in the context of stochastic resonance. So therefore, you can also use a different type of noise depending upon a prior knowledge of what kind of signal you're trying to detect.